Hey guys, welcome to Calculus Day 20. I hope you had a good 4th of July weekend, that you stayed safe and kept yourself out of trouble. Today we're going to talk about the next progression forward, which is the derivative. Now, if you're taking calculus next year, you will most likely spend your entire first quarter just on limits like we've talked about. Your entire first quarter. So that's, the first 10 weeks of school for many of you. The second quarter is spent entirely on something called derivatives and their applications, meaning up until Christmas is what you'll be primarily talking about. And a derivative, the idea of a derivative, is to answer a couple of basic questions, basic problems that exist in mathematics. The first is the idea of slope. We've talked about slope in algebra because when we talk about slope, slope is determined to be anytime you have the rate of change of a function. Now, we've dealt with those primarily with linear functions, and so the slope is consistently the same. It is constant. It has the same value at all times. However, there is another type of slope, and this is a slope that can change over time. Let's look at a basic function. So, for today, I'm going to consider the quadratic equation y equals x squared. Let's get a graph going. Make sure my graph is nice and clean. Since y equals x squared is above the axis, I've got most of my graph up there. Okay, so y equals x squared has the following points, like so. And then matching points on the other side, because it has symmetry around the y-axis. So this is our graph of y equals x squared. Now, the definition of slope, it is important to note anytime we talk about slope. Anytime we talk about slope, it is important to note that slope is the change that is taking place in the graph from left to right. So in this case, we want to talk about slope. The big thing about slope is that for this function, different things are happening at different times. For start off, let's remind ourselves, slope is defined as the rate of change of a function. We define positive slope, meaning that we are increasing over time, meaning we are going up and to the right. We define negative slope as meaning we are decreasing, or, in general, down and to the right. Notice that this particular graph illustrates both of those properties. At this dot right here, the dot -2, +4, the graph is tending downwards, meaning it would have a negative slope. Because over time, at this dot, we are going lower. We are going down and to the right. Over here at this dot, which is at +2, 4, at this dot, the graph is tending upwards. Because as we keep going to the right, we keep going up. And so at these 2 points, these clearly have different slopes. Each one of these would have a different slope. And in fact, it's the third point that would have another slope. So over here, this would clearly have a negative slope. Over here, this would clearly have a positive slope. But what happens right here at 0, 0, this would actually have a slope equal to 0. Because at this dot, we appear to have leveled off. We are not moving up or down at this point, because to the left we're going down, to the right we're going up, so in between those two, we're not doing either thing. And so there appears to be 3 different types of slopes in this one equation. And so we can't talk about slope as, the traditional m equals y2 minus y1 over x2 minus x1. That can't work, because our slope would be different here than it would be here. So we're not going to get one answer, we should get multiple answers, which is why we should get something called the slope generating function. Meaning, we're going to spend today and the entire week looking at how to find the slope not as a number, right? Because this always gives us a number answer. This is old. It's static. It gives us one number, one answer. But we're going to see this as a function where it can change, where it can become positive, where it can become negative, where it can become zero at different times using different numbers. Now, the big thing about the slope generating function is the ability to find it. One second. The ability to find that slope generating function. If you can find that slope generating function, you'll be able to take that function and use it to find the slope at these three different places. The trick is how. How do we go about finding the slope generating function, and how do we do it consistently, no matter what the function is? Because while this function is one that I can see has a negative slope here, a positive slope there, and a slope of 0 here, if I was to draw another graph, all that changes. Right? If I was to draw something like a cubic function, right? At this dot, my slope would be positive. At this dot, my slope would be negative. At this dot, slope would be positive. Here, slope 0. Here, slope 0. And so we need a way to consistently find the slope every single time. And we're going to do that by utilizing this slope generating function. Now, how do we find the slope generating function? As it turns out, you find it with a limit. That's why we spend the entire first chapter of calculus and majority of our summer talking about limits. Because if you can find the limit of a very specific function, you can find the slope generating function, and that slope generating function will tell you the slope at these points. Let's take a look. The slope generating function is found, so I like to call that S of x. Not all textbooks do. Most don't even give it a name. I like slope generating function because it's very visual. It generates the slope. So what do I call it? Slope generating function. The slope generating function is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. You might notice this looks familiar. That is because a number of homework problems have utilized this function already, because you need to be comfortable with formulas involving function notation and these delta x's. You can also notice that, and I hope your calculus teachers in the future reference this fact, this is a variation on the old slope formula. Briefly, this old slope formula can also be written another way, as delta y over delta x. In this case, they've replaced delta y with this thing, which can be found mathematically to be the same as delta y. It requires a picture and a lot of explanation we don't have time for. Note that these two formulas are the same. The only difference is this is static and gives a number. This changes and gives a function. So if we can utilize this function, we can determine the slope anywhere on this graph. Let's take a look. What we're going to do is we're going to find the slope generating function of x squared. Let's do it. We take the limit as delta x approaches 0. Now, what does this statement say? This takes the function, and everywhere there used to be an x, you're going to replace it with x plus delta x. So, instead of x squared, it's x plus delta x squared minus my original function, which is x squared, all over delta x. This might also look familiar, because again, a lot of your homework problems wanted you to start thinking in terms of these deltas and get used to working with them. That's the big detail. Well, let's simplify this. The first one, limit delta x goes to 0. Do you note if we actually try to make delta x go to 0, nothing happens. Because on top, if this becomes 0, you end up with x squared minus x squared, which is 0. On bottom, you end up with 0. 0 divided by 0 is undefined, so we know we're supposed to simplify more. That's a big detail. In this case, when I take this delta, what happens on top? We would FOIL this out. It becomes x squared plus 2x delta x plus delta x squared. That's the first term FOILed out, right? You would square and FOIL minus x squared all over delta x. If I plug in delta x, I still get 0 divided by 0, so I know I'm not finished yet. So I keep going. Limit delta x approaches 0. Well, I see here I have an x squared and a negative x squared. That's a big detail. So I can cancel those out. This leaves me with 2x delta x plus delta x squared all over delta x. If I plug it in, I still get 0 divided by 0, so I know I'm not finished yet. I keep going. I notice that the top of this can be factored, meaning I can take a delta out of both terms. This gives me the limit as delta x approaches 0 of delta x times 2x plus delta x. I know that's right because if I redistribute the delta x, I get right back where I started. But again, if I plug in 0 for delta x, I still get nothing because on top I have 0, on bottom I have 0. I'm not finished yet. I keep going. I can cancel the delta x's out. This leaves me with the limit as delta x approaches 0 of 2x plus delta x. Now if I plug in 0, I get an answer. 2x. But what is 2x? 2x is the slope generating function, meaning that if I plug in x, I will get out the slope. Let's go back to my original problem up here. This formula, so in this example, x squared has a slope generating function of 2x. Let's ask the question, what is the slope at the point -2, 4. Okay? Well, to find that, we take the slope generating function, which is 2x, and we plug in my x value, which is -2. So we would plug in 2 times -2. That tells me my slope at that point is -4. Meaning that at this dot right there, at that place, not only can I clearly see my slope is negative, but I can specifically tell you it's a slope of -4. Using the slope generating function, I just have to plug in the x value. Everywhere there used to be an x, I plug in the x value, and it will pop out the slope. Meaning, what is the slope at -2, 4? -4. Let's ask the next question. We already know its answer because we can see it from the picture, right? This is supposed to have a slope of 0. But do we get that from the slope generating function? Yes, we do. We do. Let's try it out. What is the slope at 0, 0? Well, we take our function, 2x. Everywhere there's an x, we plug in 0. Because remember, we plug in the x value into our slope generating function. My x value for this point is the 0 value, so I plug in 0. And we take 2 times 0, which tells me the slope at 0, 0 is 0. Exactly as we predicted from the picture. Meaning my slope generating function has correctly predicted 2 out of 3 slopes. Let's look at the third one. According to my picture, this should have a positive slope because it is going up over time. That makes sense. And it should make logical sense with the formula too. We should be able to get a positive answer that clearly represents what's happening at that point. Well, let's do it. So, what is the slope at 2, 4? Again, I plug in my numbers. I have my equation, 2x. This is the slope generating equation, which again we found by this process. We plugged into the slope generating function, which is a limit. We solved that limit, and output is the slope generating function, which is 2x. Now we take that slope generating function, we plug in the point, which is 2 for the x value, 2 times 2, which tells me my slope is 4, which you notice is a positive number. And notice that it actually makes even more sense, because my left-hand side and my right-hand side are symmetrical, and their slopes are matching, except for the sign. On the one side, right, it's -4. On the other side, it's +4. So it makes sense that they're symmetrical, not just in terms of their values, but in terms of their slopes. You can see how the slope generating function, this function right here, when plugged in and solved correctly, will always output a slope generating function that will allow us to find the slope for any function at any point. That is the big detail here. This function lets us find the slope for any function at any point, or any combination of points. We could find it for 50 different points. We would just need to find the slope generating function first, and then match that to the individual point. Now before we go on, I'm going to do a couple more of these, but I want to make sure to verify this with the graphing calculator that these are right answers, okay? To do that, I'm going to use something called a tangent line. This is the most common application of the slope for a function. A tangent line is simply the line that represents the slope, or remember rate of change, at a specific value or point. It is the line that represents the slope at a specific point. Now because of this, it's going to have some extra properties too. A tangent line typically only touches the graph at that point, and its tangent line, because it is a line, has a definable slope using y equals mx plus b, and the slope formula, y equals y2 minus y1 over x2 minus x1. It has a traditional slope, but it represents the slope at that place. I'm going to actually use these previous ones to find the tangent line. This first dot, so we have x squared, and I had 3 points, -2, 4, 0, 0, and +2, 4. The tangent lines for each one of these can be found by using the standard formula from algebra, y minus y1 equals mx minus x1. Now, we know the y1 and x1 because they're given by the point. So in this case, for this one, it'd be y minus 4 equals x plus 2. For this one, y minus 0 equals x minus 0. And y minus 4 equals x minus 2. The only difference is their slopes. And how do we know their slopes? Well, we use the slope generating function to find them. At this point, my slope was -4. At this point, my slope was 0. At this point, my slope was 4. And so these 4 lines should be tangent to my original equation. That's exactly what happens. Let's pull open Desmos. Okay, so I have Desmos now open. Let's look at this first line, which we have as y minus 4 equals -4 x plus 2. Oops. I don't know what happened there. What happened? There we go. Notice that this blue line represents the slope at this particular point. Let's make this a little bigger so you can see a little better. There we go. Notice how this blue line is representative of the slope here at this very specific point. The blue line represents the rate of change that is happening along the red curve as we are changing over time. Let's do another one. Y minus 0 equals 0 times x minus 0. Obviously, I could simplify this a lot in order to make this nicer to write, but I'm just showcasing how we can use the formulas to find that tangent line. Notice the green line goes through the point 0, 0, and is representative of the slope, which is a slope of 0. My other one, 1 minus 4 equals 4x minus 2. Notice my purple line represents the slope over here at positive 2. And so each of these lines represents different tangents at different points with different slopes. And we found all of them using the slope generating function, which is a limit. Let's do it again. Okay, let's do it again. We're going to find it specifically for the following function. I'm going to ask you, what is the slope of f of x equals x cubed plus 2x, and I want you to do it at a specific place, at the point 1, 3, and then secondary, I'm going to ask, what is the tangent line? What is the equation of the tangent line? So let's answer these two parts. Now to do so, we're going to have to use that slope generating function, that limit. Now this will be the hardest part of many of the problems today, is that if you cannot evaluate that limit, you cannot find the slope. So let's do the limit piece. Okay, so remember my original equation, so this was the OG, what used to be the OE, the original equation. My original equation was the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. So for this problem, that means I would have the limit as delta x approaches 0 of, I would take my original function, everywhere there used to be an x, I replace it with x plus delta x. So my original function had x cubed, but not anymore. It has x plus delta x cubed plus 2 times x, but not x anymore. It is now x plus delta x. This is my original equation, so this is that first piece, minus the actual original equation, which is x cubed plus 2x all over delta x. So this first step is key. You have to be able to plug into the slope generating function correctly to get this limit. Now, that's the first part. Part 2 is we have to actually be able to evaluate this limit, which means I'm going to have to cube this first term. I'm going to have to multiply this second term times 2, and then I'm going to have to simplify a bunch of stuff. If you are not confident with your algebra skills, and especially your algebra skills with a delta involved, take some time to practice it before you come in. Take a look back at some of these problems and try them again. Try them again. Keep trying them until you can get used to using delta x as just delta x. It is a variable by itself. It is not delta times x. It is delta x, one variable, one thing that does its own properties. Let's do this. This would become the limit as delta x approaches 0. Now I happen to know how to cube these in my head. If you don't and you're cubing them by hand, make sure you match my solutions. If not, double check your work and make sure you're getting the same answers I am. Okay? So if I cube that first term, that would become x cubed plus 3x squared times delta x plus 3x times delta x squared plus delta x cubed. That is this first term cubed plus 2 times that. 2 times x would be 2x. 2 times delta x would be 2 delta x. So here's my first thing. Minus my second thing, which is x cubed, distribute the negative, negative 2x, all over delta x. And again, I can't emphasize this enough. If I actually plug in delta x here, I get 0 divided by 0. Try it. Trust me, it works. So I know I have to keep going. If you ever have 0 over 0, something has to simplify. Keep going. So we have limit as delta x approaches 0. All right, let's simplify what I can. I have x cubed and negative x cubed, so those are going to cancel. I have positive 2x and negative 2x, so those are going to cancel. What's left behind? 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2 delta x all over delta x. Again, if I plug in delta x equals 0, then I can't get an answer because I get 0 divided by 0. I know I'm not finished yet. As you can see, though, there's a delta x in everything, so I can factor that out and simplify. This is going to become the limit as delta x approaches 0 of delta x times, okay, if I take a delta x out of this term, I'm left with just 3x squared. If I take a delta x out of this one, I'd have 3x. I take one of the delta x's out, leaving one of them behind. Take a delta x out of this one, I'd leave 2 delta x's behind. Take a delta x out of this one, I'm left with just 2, all over delta x. And now I can see my delta x and my delta x are going to cancel, leaving me with the final limit as delta x approaches 0. All those deltas disappear. I'm left with just what's left in the parentheses, 3x squared plus 3x delta x plus delta x squared plus 2. And at that point, I can actually do the limit where I plug in 0. So 3x squared is just 3x squared. 3x times 0 would be 0. 0 squared would be 0. Plus 2 would just be plus 2. So this is my slope generating function for x cubed plus 2x. This is the slope generating function. So if I want to find the slope at this specific place, what I do is I take this function, which is 3x squared plus 2, and everywhere there's an x, I would put in 1. Because, again, the point is the x value of 1. Notice that I don't even care about the y value. The y value isn't actually that important, as weird as that sounds. But that actually makes sense when you look at the picture. Because in the original picture, where you are does not have anything to do with the slope. In terms of whether you're up here or up here. You can have a positive slope up here, or a negative slope, or a slope of 0. The fact that you're high on the graph, high on the y-axis, means nothing. What matters is where you are on the x. That's what's changing over time. So, what is the slope at this specific point? Well, I take my equation, which is 3x squared plus 2. I take 3 times 1 squared plus 2. That tells me my slope at this point should be a slope of 5. That's pretty cool. So the slope at this point should be 5, and we're going to graph this in a second and see that the slope is 5. Second part, it says, what's the tangent line? Well, again, I'm going to use this formula to find that tangent line. So I do y minus the y value, which was 3, equals the slope, 5, x minus the x value, which is 1. So this would be my tangent line. Let's pull up in Desmos. We don't need these anymore. Boom, 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 boom. All right, my original equation was x to the third plus 2x. That's a pretty neat looking graph. Okay, so the point we're looking at here is the point 1, 3. So that's right there. Okay, which you can see from the graph, it clearly has a positive slope because it's going up and to the right. At this point, if we were to continue, we are going to continue upwards, which means it has a positive slope. Well, let's see if our tangent line is going to match the slope while going through that point. Here we go. It is y minus 3 equals 5x minus 1. And look at that, wouldn't you know it? We go through that one point at 1, 3, and it's clear that this red line matches the slope, right? They perfectly line up right at that point, okay? Now, in other places, it doesn't match the slope, right? Here at 0, right, it's not nearly as steep as it is there. And so it clearly has a different slope. But it still has a slope. And if I wanted to find where the slope was at 0, I would just plug 0 into this slope generating function. In fact, I predict to you that the slope at 0 is going to be 2. Because if I plug in 0, I do get a slope of 2. And I can do this for any point. And no, it doesn't matter where it's at on the axis. I can find that slope. If I go over here to -1, -1, where are you at? There we go. If I plug -1 into my slope generating function, I would get a slope of +5 again. And you can see that this red line appears to also match the slope down there, which is really cool. Like, we can find the slopes at any point using this slope generating function. All we need to do is find that function and then plug in to that function. Notice again, we plug in only the x value, so that was the 1. And with that x value, we can find the slope, and we can even use a slope to determine the tangent line. We're going to spend the next 2 days practicing using this formula to do all the problems. Now, I'm going to hand the entire assignment, or at least most of it, tonight. I do not expect it to be done. You can try to do it all, but don't expect to finish it. Because we're going to keep practicing a lot of these kinds of problems, and I'm going to do some of the hard problems with you. Because you need to get practice using this formula, the slope generating formula. Going through the process of being able to cube or square and distribute and simplify, which is algebraically intensive, but is doable, so that we can get down to the slope generating function, then use that function to actually find the slope. That is it for today. We're going to practice with this slope generating function for the entire rest of the week, so get used to seeing that formula. It's going to be a blast, I promise. Tomorrow night I will post the post-test, which you'll be able to use and solve whenever you need to. And you should have everything you need to do every problem in there. We didn't talk about limits or logarithms or exponentials, but everybody that turned in their pre-test did well in that part, so I'm not too concerned about it. But I want you to make sure that you can do things like continuity, which we've discussed, finding limits, which we've discussed, and tangent lines, which we have now discussed, which are the things that were truly just calculus. And that'll be it. Hope you guys have a good rest of the day, and I'll see you guys tomorrow.